Challenge accepted. All right, Braden, you're the man. Let's do it. All right, here you go. Why is this unit difficult? I'll tell you. I won't mix words. Quadratics, you already know how to do it. Should be a piece of cake, upside down. No problems at all. But after that, you have to learn about applications of the maximum and minimum, which will be 100% word problems. And then you will learn about function composition, which you don't know. Then you will learn about function inverses, which you don't know. So the nice thing is, up until this point, you've known most of the material that we've covered. This is really the one unit during first semester where it is really kind of new. So if you miss a day, say you're a cross-country runner that just goes to Dairy Queen instead or something, I don't know. But cross-country's over, right? So you don't have to miss any more days, right? But if you did, you got to make sure you watch that stinking video, right? I've improved the sound, and I'll give shout-outs to you if you're not here. So Jake from State Farm, kudos to you, man. Check up on the video. You're a smart kid, we think. All right, let's do it. So extreme values, as you look at this function, we call this, in calculus, we call it a local maximum. And it is not the largest spot on the graph, but it's the largest spot in its immediate vicinity, okay? So for those values right around it, it's bigger than everything else. And this spot we call a local minimum. Now, have we found these locations using our calculator already? Yeah. Okay, so what's the big deal? Well, the fact is that obviously quadratics have these maximum and minimum values. And there's great application for them. When I was at St. Olaf, my first calculus teacher, his name was Mike, and he used to work for the Mayo Clinic. And when he worked at the Mayo Clinic, he would listen to doctors that would come in and talk about issues that they were having with their patients. And they would try to find ways to solve problems. So Mike, one day a doctor walked in and said, "Hey, Mike, I need your help." Mike said, "What are you doing?" He's like, "Well, dude's got a clogged artery." It's like, "Okay, I don't know how to fix that. Like, I think you're supposed to do like a bypass or something." He's like, "Yeah, I need to do bypass." So that's important. Otherwise, it'll just explode eventually, right? That's called a heart attack. Bad news, right? Especially in America. We got a lot of heart attacks because we have highest rate of heart disease because we don't really exercise and, we eat a lot of, red meat and stuff like that. So whatever. A lot of salt, okay? So what do? Is you bypass it. And the doctor came to me and said, "Here's the deal. I'm going to bypass it, but I need to know this." He said, when the blood flows down here, it ends up kind of, making its way finally to this branch, but it causes a lot of friction on this joint right there. And so he's wondering, at what angle should I place the artery in order to minimize the viscosity of the blood flow? Viscosity would be the friction of the fluid. Does that sound like an important question? Like if you're the dude having the bypass surgery, and the doctor said, "Hey, just want to let you know, I put it at an angle so that the viscosity of the blood flow would be minimized." I mean, you'd be like, "Okay, sounds like my doctor knows what he's doing, right?" That's a pretty big deal. And so sure enough, Mike was able to come up with an equation, and that equation had a graph, and that graph had a minimum. And so he was able to minimize the viscosity of the blood flow. It was good news, and it's a classic problem moving forward that a lot of people use. So does this have real life application? Oh, yeah, without a doubt. We're not really ready to handle that kind of a problem, but we might cut somebody open. Just experiment. Any volunteers? All right, Braden. Cool. We'll do it. So the maximum and minimum problem becomes very obvious when we are dealing with quadratics. They all have maximums and minimums. This is in what we call vertex form. And as we look at the graph of a parabola in vertex form, it has a certain location for its vertex right here. In fact, that vertex is found by a horizontal shift and a vertical shift. Anybody want to guess what the location of that vertex is? You just tested on this. Terry, loud and proud. Come on, own it. HK, all right, a horizontal shift of H and a vertical shift of K. So its extreme value would be K. That'll be either the largest or smallest number on the parabola, depending on whether the a value is positive or negative. So we're actually going to look at vertex form tomorrow. Today, we're going to look at what we call standard form. And standard form is ax squared plus bx plus c. And as we look at that parabola, it as well has a vertex that is at the extreme value, either the maximum or the minimum. Anybody remember how we find the vertex if it's in standard form? Come on, you're the best of the best. You already know it. What? Yes, negative b over 2a. Nice job. And here's why you already knew that. You know the quadratic formula, don't you? So if you know the quadratic formula, you recognize that quadratic formula can be rewritten as negative b over 2a plus or minus the square root of b squared minus 4ac all over 2a. If I just separate in two fractions, what does that do? Well, it takes negative b over 2a, which is the x value of your vertex, and then it simply tells you to add a certain amount and subtract a certain amount in order to find the x-intercepts. So the vertex is right in the formula for the quadratic formula. See it? Cool. We should like applause every time we see something we like. So, all right. So the extreme value is going to be the y value. How do we find the y value of the vertex if the x value is negative b divided by 2a? Yeah, you're going to plug it in. F of negative b divided by 2a. So the extreme value is f of negative b divided by 2a. And we'll get to that application later on. Flip it over 2 pages. And you can see you have this sheet right here. This is a nice summary of the properties of parabolas. You can see that today we're focusing on standard form. Ax squared plus bx plus c. If a is positive, it goes up. If a is negative, it goes down. We talk about the vertex, negative b divided by 2a, and f of negative b divided by 2a. Axis of symmetry divides it in half. It is a vertical line, and it will be x equals negative b divided by 2a. Always the x value of the vertex. The y-intercept, super easy. It's always just this constant right here. Because when you plug in 0, that's what you get. And then for finding the x-intercepts, we can either factor or use the quadratic formula. And that's what we're going to roll through today for 2 examples. And you have a nice worksheet. So let's set this up. I'm going to identify direction. It says sketch a graph and given a parabola, state the coordinates of its vertex and intercepts. I'm going to do a little bit more than that. We're going to identify the direction, the vertex, the axis of symmetry, the y-intercept, and the x-intercepts. Okay? Cool. So, direction, up or down? It would be up. What? Okay. Vertex. I take negative b divided by 2a. What's the b value? y0. Thought it was negative 8. There's no x term. There's no linear term. So b is the number in front of x. There's no x, so it's 0. Divided by 2a, 4. So vertex, x value is 0. What do I do now to find the y value? F of. So plug it in. 2 times 0 is, or 0 squared is 0 times 2 is 0. Minus 8 is negative 8. I will make my graph because I like to see what it looks like. Plot my vertex 0, negative 8. Axis of symmetry. If you were to write this on the test, I will award you 0 points. Because the axis of symmetry is not, well, A, that's totally wrong. It's not negative 8. If you wrote 0, I would still say that that's incorrect. You need to write an equation. X equals 0 because it's an equation for a line. You need to understand that it's actual line. So I need the X equals. Okay? So don't make me take off points there. All right. Y-intercept. Negative 8. X-intercept. Got two options. I can either factor or use the quadratic formula. Does it factor? It does. 0 equals 2x squared minus 8. What do I factor out? Dose. X squared minus 4. 0 equals 2 times x minus 2 times x plus 2. X is plus or minus 2. I plot those. As you can see, they are equally displaced on each side of the axis of symmetry. Draw my graph and get a beautiful looking parabola. If you wear contact lenses, your contacts are parabolas. Yep. There's actually an equation for your contact lenses in parabola form. Yeah. Okay, any questions on that one? That was easy, right? You want to try a hard one? Let's try a harder one. Y equals negative 1/4 x squared minus 6x plus 3. We're going to talk about direction. We're going to talk about vertex, axis of symmetry, y-intercept, x-intercept. Made an apple pie on Saturday night. Oh, it was so good. Yeah, oh yeah. Oh, yeah. Had a crumb topping instead of like a bread topping. Oh, Dutch apple pie. Oh yeah. Oh. Yeah, scratch. Yeah, I used some apples off the trees, but then I also used some Granny Smith and some Honeycrisp. Perfect blend. Oh, yeah. All right, direction, up or down? Down. Why? It's negative. Yep, there you go. Vertex, negative b. What's negative b? 6 divided by 2a. What's 2 times negative 1/4? Negative 1/2. Yeah. And so 6 divided by negative 1/2, I will multiply by the reciprocal and get negative 12. Okay, so I've got negative 12. How do I find the y value? Plug it in. Negative 12 squared. 144. A fourth of 144. 36. Make it negative. Negative 6 times negative 12. Positive 72 plus 3. So negative 36 plus 72 is 36 plus 3 is 39. All right, so I should start making my graph. So I'm going to make my y values go up by 10. Make my x values go up by 5. And plot that negative 12, positive 39. Okay. Axis of symmetry. Equation for axis of symmetry. If you don't write the x equals, I mark it wrong because I'm a jerk. What? No! Y-intercept, 3. Trace. The y-intercept is always the constant on the end. 3. Stop laughing, Jenna. All right. So if I know that point, can I figure out another point? How? Yeah, I go 12 on the other side, reflect it over. So reflect it over the axis of symmetry. So it would be 12 units the other way. So it would be like negative 24, positive 3, right? Cool. Now the big one, x-intercepts. How to find x-intercepts? Instead of equal to 0. 0 equals negative 1/4 x squared minus 6x plus 3. Quadratic formula, awesome, but I hate the fraction. Yes, multiply through by negative 4. So 0 equals x squared plus 24x minus 12. But don't multiply through by negative 4 at the beginning. If you did it at the beginning, you'd be multiplying y by negative 4 as well, right? That's kind of illegal. I mean, you would end up thinking that the y-intercept was negative 12, and it isn't. You only multiply through to get rid of the fractions when you are finding the x-intercepts, because 0 times negative 4 is 0, and that's the beauty of it. So, quadratic formula, your favorite thing. X equals negative b, negative 24, plus or minus, square root of, against, what's 24 squared? Starts with a 5, ends in 76. Nope. All right, 576. Minus 4 times a times c divided by dose. So, what do I have in the discriminant? Discriminant is the portion underneath the square root. $624. Now, is 624 a perfect square? Nope, 625 is, shoot, missed it by 1. But what if you ended up with a negative? Square root of negative, what does that mean? Imaginary. What does that mean graphically? If you have an imaginary solution for your x-intercepts, that means it doesn't cross the x-axis. In this situation, are we confident this crosses the x-axis? Yeah. And so we know that then we would have made a mistake in our discriminant to come up with a negative value. However, suppose instead of going down, suppose the graph went up. Then would it cross the x-axis? And we should get an imaginary number within our solution set for x-intercepts. So let's solidify this. We got x is equal to negative 24 plus or minus the square root of 624 all over 2. Can you simplify the square root of 624? I bet we can. I bet it's divisible by what? 16? Yep, 16 and 39. Nice job. So we've got negative 24 plus or minus 4 roots of 39 all over 2. Does that simplify? So for your assignment and on your test, you will have to express your answer for your x-intercepts in simplest radical form, so negative 12 plus or minus 2 roots of 39, and you'll have to express them as decimals. Why would I want to express them as decimals as well? So I could graph them, because I want them to be around negative 25 and around 0. In order to make sense with my graph, that's about what they should be, right? So we take out the handy-dandy calculator, and we go negative 12 plus 2 roots of 39, and I get 0.49. So that's pretty close to 0. And if I take the same entry, and instead of a plus, I change it to a minus, I get negative 24.49, which is close to the 25 value that I wanted. So it looks like these are my x-intercepts. So now I can make a nice sketch of my graph. There is another way of coming up with the decimal for the x-intercepts. How? We could use technology. How? Did anybody go to YouTube and watch my little video, 4 minutes and 2 seconds, on how to type your quadratic formula in your graphing calculator? Nobody? You're my only class. I'll look it up for you right now. So all you have to do is just press program, enter A, B, and C, and it'll spit out the values for you. That way you can quickly check your answer. There you go, guys. There's quadratics in standard form in a nutshell very quickly. Your assignment, I will hand out to you now. Rhiannon, we missed you today. You too, Jake. See ya.